Well, let's start the demo. The demo is built on a single node server. It can be a physical server or a virtual machine. The host system has been pre-configured. It includes Docker, Golang, Kind, kubectl, and Helm. Installation configuration can be done manually or by using a script. We have an Ansible playbook to automate that process. In the next step, a Kubernetes cluster is created with the NSM deployed on top of it. We have prepared a custom bash script called incrementally, which handles that process. The script has already been run. The kind-based Kubernetes cluster and NSM are ready. So now let's take a look at the Kubernetes objects which are present in the cluster. Please note that there are NSM-related objects in the NSM system namespace in addition to the standard. By checking the Kubernetes custom resource definition present in the cluster, we can see the NSM ones defining endpoints, NSM managers, and network services. Another script called phases mgtsh is used to manage different steps which are called phases. There are 7 phases in total, from 0 to 6, and we'll execute them sequentially during the demo, explaining and showing the obtained outcomes. By going through all of them, we get the target setup with the defined NSM network service and NSM clients and endpoints deployed. We include here the clients and services pods as well as the CNF pods based on our custom UCNF image. Additionally, we have etcd, Prometheus, and Grafana pods. We call them FCAPs. Now we will execute phase 0, which adds a network service named demograph to our cluster. Now let's check the network service we have created. There is one network service, demograph. So now let's take a deeper look at it. This definition uses the NSM v0.2 API version, which is v1 alpha 1. We can see that the demograph network service uses an IP as a payload type. The network service defines the forwarding rules used in the demo. We talked about those rules before. Here is an example usage. Before going back to the slides, we'll execute the script for the next phase. This is a deployment of the FCAP pods. As we mentioned, there are 2 bash scripts which contain functions allowing us to build an NSM environment and then to execute all the phases one by one. The infra-mgtsh script is responsible for creation of a kind cluster consisting of 3 nodes. So these are NSM control plane plus NSM workers. Deployment of the NSM system in version 0.2.0 using NSM Helm-based installer. Downloading of upstream Docker images like NSM components images, images for monitoring, the Alpine image, etc. Building the custom images we use, and loading the required images into the kind cluster. There's also one step being realized beyond the script. This is building a custom VPP agent image. In our case, this build is not done locally, but it is integrated into our external CI pipeline, meaning we first need to download the image before we launch the script. The phases mgtsh script in turn is a helper tool facilitating the phases management. This includes creating appropriate pods, configuring them, and testing how they behave. There are 7 phases in which we'll add components into the setup, and the order matters. So phase 0 is about creating the network service. Phase 1 is for deploying what we call FCAPs. This is etcd for configuration management, Prometheus for monitoring, and Grafana for data visualization. In phase 2, we deploy client 1, service 1, and the Flow Classifier CNF. In phase 3, we deploy the NAT, the firewall, and the external gateway CNFs. In phase 4 and phase 5, we deploy service 2 and service 3 respectively. And in the last phase, which is phase 6, we deploy service 4. In fact, 3 instances are deployed in total. And additionally, we deploy the last CNF, which is the load balancer. Let's get back to the console to check the status of phase 1. There should already be present pods with etcd, Prometheus, and Grafana. So you can see them here, as well as the corresponding Kubernetes services that have been created for them. Now let's go to the Prometheus and Grafana dashboards. We'll start with Prometheus to check the status of the targets it is supposed to connect to. Please note that there is no target available at the moment, as no CNF has been deployed yet. Now let's log into Grafana Web UI. So we'll provide the credentials. The first thing we need to do is to select the right data source. So we click Prometheus as the first option. And now we need to provide the right URL. For that purpose, we'll use the service created in the Kubernetes for Prometheus. So as you can see, it is called fcaps Prometheus -svc, and the value of the port is export, which is 9090. So we'll provide all of this as a URL, and now it's time to check the connection. So okay, as we can see, the connection to the Prometheus has been established. Okay, this is enough for now. We'll get back to Prometheus and Grafana later on. Now it's time to start phase 2. In the meantime, while its components are being created, let's discuss its scope. The key CNF in our setup is the Flow Classifier. As its name indicates, it is responsible for flow classification, and based on that, appropriate actions are taken. In the Flow Classifier, we use Ligato ACL and ABF plugins for its proper configuration. In this phase, we also use Client 1, a pod emulating request coming from the client's application, and Service 1, which is a TFTP server. Now let's look at the ABF mechanism in a little more detail. The ABF stands for ACL-based forwarding. To better understand it, let's look at an example scenario. We have a forwarding element to which the packet arrives. Typically, a forwarding element reads the packet header to get its intended destination. Next, it compares the destination IP address bit by bit with entries in the internal routing table. The entry which has the longest number of network bits matching the packet's destination IP is the best match. This method is called the LPM, longest prefix match. With ABF, it works differently. ABF relies on the ACL, Access Control List. ACLs are used to match traffic and specify actions for selected packets. Selection can be based on different criteria like destination IP address, source IP address, destination port, source port, protocol. The ACL plugin also supports macros, though it does not support mixing IP and macros. Anyway, you can selectively specify criteria to match intended packets. Then you decide what you want to do with such a packet. For this purpose, actions are defined. Ligato supports the following actions: deny, permit, and reflect. The forwarding node has several interfaces which are used to connect to other network nodes. We can define the input interface and the output one, which also identifies the next hop, a network node connected to the output interface, in fact. All these parameters together compose a single instance of ABF. So once again, the ACL to match the packets based on information from the packets themselves and to specify an action. The input interfaces at which incoming packets will be examined against the configured ACL. And lastly, the forwarding destination, of course, when the action is equal to permit. Otherwise, it doesn't have any sense. And this covers output interfaces and the next hop IP address. After introducing ABF theory, we can get back to our demo. The phase 2 configuration is done by our script, which has to set several items. The client's one pod initially has a default route set to the Kubernetes CNI interface. In our setup, we want to change it to the NSM interface. To accomplish that, two actions are performed. First, an existing default route is deleted, and then a new default route is added. We also need to configure a new route for the Service 1 instance, which is the TFTP server. Here we set it up so that all traffic to 10.60.0.0/16 should be forwarded through the NSM interfaces with the next hop set to the Flow Classifier. The 10.60.00/16 pool is shared by the CNFs acting as NSM endpoints. Each CNF uses a different subnet specified in its Kubernetes manifest. Each such subnet is further broken down into smaller subnets for individual connections with the NSM clients, client 1 and services from 1 to 4. Now our client and service 1 have their routing configured. They can talk to each other. However, we want to have a more strict forwarding scheme. For that, we add to the Flow Classifier a rule for traffic coming from client 1 destined for any internal NSM related IP with the action deny. This is done through an ACL. The next step is to define the ABF. The ACL it reference has been already configured. Now we need to specify an input interface. This is the one to which client 1 is connected. In this particular case, it doesn't make sense to indicate a next hop as the ACL is configured with a deny action, which means we want to block the traffic, not forward it anywhere. Finally, we give this ABF a priority equal to 35. We are using ABF priorities, which are a simple way to order ABF when they reference the same input interface. This is the case with our setup, which you will see when we discuss the configuration for the next phases. The general rule is that the lower the priority number ABF is assigned, the more important it is. In the current phase, we want to make it possible for client 1 to download content from the TFTP server. For that, we need to add another ABF to the Flow Classifier. So first, we need to configure a new ACL permitting UDP from an IP address of client 1 destined for the IP of service 1. Next, we add ABF using this ACL. We specify the same input interface as for the first ABF, but this time we also need to define the next hop. As you can guess, it will be service 1. Finally, we set the priority equal to 15. The ABF with priority 15 is processed before the ABF with priority 35. This is the one with a deny intent. It means that UDP traffic from client 1 will match the rules specified in the ACL the second ABF is based on. As a result, such traffic will be forwarded. Any other traffic originating from client 1 to any IP address from our internal NSM pool will be discarded due to the first ABF. On the reverse path from service 1 to client 1, there are no rules for the Flow Classifier. The standard routing-based forwarding is executed instead. Now let's see how the Flow Classifier and other CNFs are configured in practice. We use the etcd-ctl tool to update etcd key value store, which holds the configuration for all CNFs. Ligato specifies keys to be used to manage configuration of different plugins or models. Based on those models, we created configuration entries for our setup. In phase 2, the Flow Classifier configuration is as follows. Here we can see the first ACL blocking the traffic from client 1 to any IP address from internal NSM pool, and ABF referencing to this ACL. And then another ACL to allow UDP from client 1 to service 1, and then the second ABF. Now maybe a comment on how we deploy the TFTP server. Let's take a look at the service 1 manifest. And as you can see, it has a volume mounted where we add 3 simple files directly via config map. And these files are the content that can be downloaded from the server. Okay, now let's check the pods in the default namespace. As you can see, 3 new pods have been created: client 1, service 1, and Flow Classifier. Now we'll test if client 1 can download anything from the TFTP server. Yes, it is working. You can see the content of the first file displayed on the client's 1 console after it has been downloaded from the server. As we know, it was possible thanks to the proper configuration of the Flow Classifier. So first, let's check the Flow Classifier interface is configured by NSM. The first interface is connected to the client 1 pod and the second to the TFTP server pod. Now let's check the config that has been added to the Flow Classifier through etcd. You can see 2 ABFs and 2 ACLs. And now we can retrieve the full Flow Classifier configuration using agentctl utility. As we remember, this is the tool which is offered by Ligato VPP agent. So here you can find the ABFs and ACLs configured. And here are interfaces configured by NSM. Okay, now let's attach to the client's 1 pod. First, we'll check the IP address and routing. Yes, this is the IP address assigned by an NSM system. Now let's check the routing. We can see that the default route is via the IP address which is connected to one of the interfaces on the Flow classifier. And then we'll try to ping the Flow classifier. It is not working because of the rule deny any traffic to internal NSM IPs. But this does not affect TFTP traffic to service 1. Finally, we'll try to download 2 other files from the TFTP server. So as we can see, we are able to download the file 2.txt. And now let's try to download another file. Yes, it is possible also to download the file 3.txt. Okay, maybe let's display the content of the second file. Okay, we did it. Everything works fine. Now let's go to Prometheus dashboard to see if anything has changed. And now the Flow classifier target is available. You may remember that each CNF in our setup has its own Kubernetes service configured. Using the metrics path on the port from which we have an SSH tunnel to the Flow classifier service established, we can list all the metrics that can be exported to external monitoring and management tools. For instance, we can check the total number of bytes transmitted on the given interface of our CNF, which is the Flow classifier in this case. Now let's go back to Grafana to visualize this. For that, we'll create a new dashboard. And we'll define a new query. This will show the total number of bytes transmitted by the Flow classifier on the MEMIF 1/0 interface towards clients 1 pod. So this is the example of how you can realize a monitoring system for CNFs. We'll go back to Prometheus and Grafana in the next phases. Okay, and this completes phase 2. Now let's run our script to launch the next phase. In phase 3, we are adding the NAT, the firewall, and the external gateway to our topology. This enables connectivity to the outside world. It means to the internet. What is important is that we want the traffic coming from client 1 to go through all those components in a specific order. Now we'll try to explain the details of the scenario. Client 1 should have connectivity with the internet. In the previous phase, we added 2 rules to the Flow classifier for client 1. One allowing TFTP-related traffic to access service, and the second, with a lower priority, blocking the traffic to any internal NSM IP address. Now we need to specify a default rule for client 1. We say default because it needs to match any destination IP address. So first, we create an ACL with a destination IP set to zeros, the source IP set to client 1 IP, and an action set to permit. Next, we add ABF with the following parameters. As an input interface, we indicate the one connected to client 1. The next hop is set to the NAT, and the priority is set to 40. It is the lowest priority value we have set so far, and it is important as this rule has a very wide scope, any destination IP, any protocol, any port. It's perfect for describing internet traffic, but it is a bit dangerous because it has a wide field of influence. Because any packet received from client 1 will match. Fortunately, thanks to the priority setting, this rule will be used as the last in our rule list, when no other rule matches. Now it's time for the NAT. It is directly connected to the Flow Classifier and to the firewall. To be able to communicate with client 1 and the internet, it requires routing entries. So first, a route to the client, 10.60.1.0/30 via the Flow Classifier, and a route to the internet, a default route via the firewall. We also configure the NAT itself. First, the NAT pool, so the first and the last IP address. Then the NAT inside and outside interfaces, so in this case, towards the Flow Classifier and towards the firewall respectively. And NAT static mapping. Here we want the client 1 IP address to be mapped to the external address 10.199.0.102. For the firewall, we need to add the following routing entries. 10.199.0.0/24, which is the subnet the NAT IP pool belongs to be reachable via NAT, and the route to the internet, a default route via the external gateway. Let's look at the external gateway now. It requires routing to the NAT IP pool, so we add such an entry. The external gateway is responsible for connecting NSM internal traffic to the outside world. For that, we connect the NSM to the host interface using the Linux VFPR. By employing the Ligato Linux plugin, we create a VFPR and assign an IP address to the host interface. We also add a VPP interface, which is attached to the second VF end. What is still missing is routing at the host level, so we add a route to the NAT IP pool. The second missing element is the source NAT configuration at the host level. We set it up using IP tables. And finally, we configure a default route for the external gateway. Now let's look at how all of this should be reflected in the configuration path to the etcd. Here we can see the ACL allowing client 1 to connect to an IP address and the ABF using that ACL. Next, NAT configuration, including NAT interfaces, NAT pool, and static mapping. Now there's routing for the NAT, routing for the firewall, filtering performed by the firewall. We will discuss in a moment. It has not been applied yet. And finally, all different pieces of configuration required on the external gateway. Okay, so let's check the objects which have been created. As you can see, the NAT, the firewall, and the external gateway have been added to our network topology. Now we'll execute the internet connectivity testing for client 1. This is a simple test based on ping and CURL. It seems everything works fine. The initial firewall configuration is set to forward packets based on routing entries. However, in real-life scenarios, the firewall performs some filtering. Thus, we also want to add some rules to it. For example, to block client 1 connectivity to the Google DNS IP address, which is 8.8.8.8. Previously, we have set static mapping on the NAT for client 1, so the traffic from client 1 from the firewall perspective has an IP address of 10.199.0.102. Using an ACL, we can block traffic coming from that address that is destined to Google DNS. So we add two rules, one to deny such traffic and a second to permit any other traffic. Okay, so let's add the filtering. And now let's make internet connectivity test again. You can see that client 1 cannot ping the Google DNS now. Okay, so let's attach to the client 1 pod now. We'll ping Google DNS once again. It's not working as expected. And now we'll try to ping another public IP address. It's working. You can see that client 1 cannot ping the Google DNS, but it can ping any other IP from the public internet. So the firewall works according to our expectations. Now let's check the CNF status in Prometheus. We'll refresh the Prometheus page. And then we can see that 4 CNFs are available right now. Now let's switch to Grafana Web UI. We'll define a new query. But this time we'll start with something a little bit more generic than before. We select the VPP underscore interfaces underscore TX underscore bytes metric like we did last time, but now without any specific parameters. You can see the list of all interfaces for which this metric is available. Since we have 4 CNFs, each having a couple interfaces configured, you have many options to choose from. Let's assume we want to pick the Flow Classifier interface towards NAT and the NAT interface towards the firewall. We should be able to observe traffic on these interfaces because we left client 1 constantly pinging one public IP address, as we remember. Now, let's identify the interfaces we want to choose. For that, we need to check the interfaces configuration on the Flow Classifier and the NAT. The NAT has been attached as a third NSM client to the Flow Classifier after the client 1 and the service 1 pods. So the Flow Classifier interface towards NAT is marked as memif 3.3/0. The similar way we check the NAT interfaces. Here the second interface is the one we are looking for. It is marked as memif 2/0. Okay, now let's go back to Grafana to choose the right interfaces. And now we can see only 2 plots, one for each interface we selected. Okay, let's leave it now. We'll get back to this later on. Okay, phase 3 has been completed. Now let's move to the next phase. First, we'll launch our script with the appropriate arguments.
In phase 4, service 2 has been added. It is a simple HTTP server that responds to requests sent by client in the form of reply echo messages. Contrary to the case of FTTP server, which is reachable by our client directly through the Flow Classifier, the path between the client and the HTTP server includes the firewall, which performs additional filtering. Let's now discuss the configuration for this phase. The route to 10.60.0.0/16 via the firewall has to be added to the service2 instance. On the flow classifier, we need to configure a new ACL that permits TCP traffic from client 1 to service 2. Next, new ABF has to be created with the following parameters. ACL, the one we configured just a moment ago. The input interface is the one towards client 1. The next hop is the firewall, and the priority is equal to 20. On the firewall, we add a route to the client 1, IP address 10.60.1.0/30 via the flow classifier. Then we turn on the firewall. The HTTP server running on the service 2 pod is configured to listen to 5 different TCP ports. What we want to do is to allow client 1 to have access to only one of those ports. Suppose we decide it will be TCP port 8082. The TCP requests to any other ports must be denied. Filtering rules will be added in a moment. And now we are taking a look at the configuration for phase 4. So, as usual, at first we are configuring ACL and then corresponding ABF for it. Next, we configure routing on the firewall. And finally, we are adding ACL rule on firewall, allowing only TCP 8082 port to be passed. Now, we'll look at our setup to see if the above configuration has been properly applied. First, we see new pods has been added. Then let's test connectivity from client 1 to service 2. Okay, we've checked the different ports and port 8080 and 8082. Both of them are working. This is because we have not yet configured the firewall rules. Let's do it now. And repeat the test. The result is different. As you can see, traffic to port 8080 is blocked, but traffic to port 8082 is still permitted. Okay, let's launch phase 5. Phase 5 introduces an NTP server to our topology. It is marked as service free. We assume that the client can access the server directly via the flow classifier. So we're taking exactly the same approach here as we did with the service 1. But that's not all. The NTP server needs to synchronize with other servers on the internet. Therefore, another link has been created between the server and the NAT so that the server can access the internet. Now let's take a look at the configuration. It is important to properly configure the routing to the NTP server instance. First, we set the flow classifier as the next hop for the client 1 subnet. Next, we reconfigure the default route. We set the next hop to be the NAT, having removed the previously set next hop. Next, we add a new configuration to the flow classifier. We are adding a new ACL that only permits a UDP destination port equal to 123 from the client 1 IP address, destined to the service-free IP. This is the standard UDP port used by the NTP protocol. We then create ABF that references this ACL. The input interface is set to the one towards client 1. The next hop is service-free, and the priority is set to 25. And the last thing to do is to add a new static mapping to the NAT. Here we say the service-free IP address will be NATed to the external address equal to 10.199.0.3. Okay, let's take a look at the phase 5 configuration which is added to etcd. At first, we are adding ACL which permits NTP traffic, so port 123. Next, we are configuring corresponding ABF. And finally, we are adding configuration for NAT. First, setting interfaces, and then we are adding static mapping for our service and corresponding external IP address. Okay, let's see the pods. We see the NTP pod has been created and is running. Okay, and let's test the service. In the first test, client 1 asked the NTP server for the time checking, and we see that it is getting a response. And the second, we are showing information about current time sources of the NTP server. So we see that it is synchronized with the sources from the internet. Okay, let's check the service free itself. So we are logging into service free pod. Okay, and let's ping 8.8.8.8. Okay, we can ping. It is different than from client 1, but it is because the deny rule was only set to client 1. And now let's also ping 1.1.1.1. And for now, we'll leave it like that. Let's move to Grafana. And we are seeing interfaces which were configured previously. So the interface from Flow Classifier and the interface from NAT. On the graph, you can see that the traffic on both interfaces for the long period was the same, meaning that the same number of packets was flowing for both components and both interfaces. But for the last few seconds, there is a difference. The traffic on the NAT interface is higher. There are more packets than on the interface on the Flow Classifier. This is because we just configure ICMP traffic on service free, and that traffic is going only through NAT and is not going through Flow Classifier. And that's the reason for the difference seen on this graph. Okay, now let's prepare our setup for the phase 6. And while it is being configured, let's introduce phase 6. In the last phase, we run another HTTP server. Here, however, we will have as many as 3 instances of it, instead of a single one, as was the case for the service 2. Therefore, between the Flow Classifier and these three HTTP server instances, we insert the load balancer. As a result, each request coming from the client will be handled by only one instance of the server at a time. We start as usual with the routing configuration. We need to add a route to 10.60.0.0/16 via the load balancer. This has to be done for each service 4 instance. Now let's move to the load balancer. First, we need to add a new entry to its routing table saying that the client 1 subnet is reachable through the Flow Classifier. Now it's time for the load balancing. Our load balancer works in L4 mode. The load balancing mechanism is provided as an advanced NAT configuration. As before, we need to create a NAT pool and mark the relevant interfaces as NAT inside and NAT outside. We also configure the NAT static mapping. This time, however, we extend the local IPs list to 3 items. Each of them corresponds to the IP address of a given service 4 instance. What's more, for each of them, we also configure the TCP port and the probability expressed in % that it will be elected by the load balancer to handle a given request coming from the client. And finally, on the Flow Classifier, we are adding a new ACL that permits the TCP from client 1 IP address destined for the external IP of service 4 that has been configured on the load balancer. We then create ABF that references this ACL. The input interface is set to the one-to-one client 1. The next hop is the load balancer, and the priority is set to 30. Let's take a look at phase 6 configuration, which is put into etcd. First, we add ACL and ABF for a Flow Classifier. Next, we move to configuration of load balancer, starting with adding routing entry for it. And next, we are configuring load balancing as advanced static mapping, NAT static mapping configuration. Let's check the pods if new one has been created. And we see 3 instances of service 4. Let's now test the phase 6. We are doing, we call it load balancer test because we are sending the same request to the IP address of which is a load balancer IP address, and we should get responses from different endpoints. And we can see that there are different endpoints here with the ending 5, ending 9 IP address, and 1. So each of service 4 instance has replied to our requests. So now we have all service instances and all CNFs running. Using the NSM, dedicated links have been created between selected objects in our network topology. The CNFs have been properly configured to allow the client to access all services. This is represented by the service function chain shown in the picture. Finally, let's look at the Flow Classifier configuration, which is part of all the service chains. It is directly connected, thanks to the NSM, to 3 other CNFs and 2 service instances. And of course to the client too. The configuration of the interface towards the client is crucial for handling requests that are coming from it. As we know, this is done using the ABF mechanism. Here we have the configuration that applies to it. In this context, priority assignment are very important as they enable the configured ACL to be triggered in the correct order. Okay, and now let's go to terminal and see the configuration which has been applied to the flow classifier. We can see that all the ABF we discussed before are set for the flow classifier, and they are already put in the proper order, with starting with ones with the lowest priority number. So okay, and this completes our setup.